Good morning, good afternoon, and good evening. I'm Tom Concolino, and I'm here with our presenter, Simon Bates. Thank you all for attending Rigaku's webinar on total diffraction and amorphous material characterization. First, a little housekeeping. Please submit questions via the Q&A button at the bottom of your screen, and we'll answer questions at the conclusion of the presentation. Now, I won't be monitoring the raised hand function, and I'll be posting relevant links in the chat window. Now, we'll be trying to answer as many questions as we can at the conclusion, and any questions that we do not get to, we will answer after the session is complete. If for whatever reason you have difficulty viewing the presentation live, please note it is being recorded, and you'll be able to view the recording hopefully tomorrow. And with that said, I'll turn it over to Simon.
Greetings, everybody. Thank you for attending what is the third webinar in our series of advanced diffraction techniques for pharmaceutical sciences. And in this one, we're going to explore total diffraction in a little bit more detail and briefly touch on some characterization for amorphous material. So total diffraction really opens up a very different way of looking at diffraction data and offers you many different analytical pathways that are really not available using traditional Bragg diffraction approaches. Now, the discussions today really follow on from the first webinar in our series, where we talked about standardless quantitative analysis and how that is possible, again, using total diffraction. It's a fundamental parameters standardless quantitative approach. But I was asked to talk a little bit more about what is total diffraction and how it differs from regular diffraction. So you receive what you asked for. So we're going to be looking into total diffraction in a little bit more gory detail. So what we'll discuss today will be total diffraction from the perspective of water. And this is something I put together for Long Island University as part of the solids course I give there. And we've also recently given this at the Rutgers University as part of a PDF training. And I'll remind the audience that we do travel around and give seminars and training schools. And if you'd like us to come and speak at your facility, then please feel free to reach out to us. And then after we've gone through what total diffraction is, we'll touch on application for unknown amorphous materials. And to me, that's probably the most interesting part of total diffraction. It allows you to characterize completely unknown materials. Let's say you're working with an intermediate, solid dispersion, that's an amorphous, there's multiple amorphous forms in there. If there's some sort of chemical reaction or interaction that's going on inside that, it could be forming something completely new. And total diffraction is a way to get a handle on that and to quantify the variability inside the sample. And finally, at the end, I'll briefly touch on the application of PDF using small box methods. Now, if you follow PDF, pairwise distribution function analysis, you'll probably see there's a lot of publications on big box methods, large box methods like reverse Monte Carlo, which we have in our Smart Studio 2 software, by the way. But in this one, I want to touch on something a little differently, which is small box models. So why is this important? It's important because X-ray powder diffraction is generally regarded in the pharmaceutical sciences, at least, as the gold standard with respect to the characterization of crystalline solid forms. But with the prevalence of non-crystalline forms, amorphous materials, mesophasics, so Condis crystal, liquid crystals and the like, nanophases, etc., traditional Bragg peak crystalline methods become less relevant. In fact, you can't really apply them in a meaningful way to a lot of materials that are becoming the standard materials in pharmaceutics. In fact, I was at the AAPS last week, and I noticed I met a number of you there at the AAPS. And one thing that really surprised me this time was the huge amount of nanoformulation, either companies providing that or discussions about nanoformulation, nanoparticles, nanocrystals, and all of that fits in perfectly with total diffraction. If you want to study these new sorts of delivery systems using diffraction tools, then you're going to need total diffraction to understand them. And total diffraction combined with component analysis provides really a very potent alternative for the characterization of complex materials. And you don't have to find peaks, which is always a plus. So now we'll go through the water story. As I mentioned, this was put together for Long Island University as part of a solids course I gave there. But I gave recently at Rutgers and partially at Rice University as well. So we travel around and we give these seminars to various places where people want to understand more about total diffraction. So feel free to reach out to us if you'd like us to put together a seminar for your team. So this story starts at high temperature, and it's about water. So we have oxygen and hydrogen floating around in some sort of gaseous state at high temperature. Of course, this is highly a conceptual model. This probably wouldn't happen in reality, but it's a starting place where we can consider total diffraction. So we shine our X-rays at this gas of oxygen and hydrogen at relatively high temperatures. So no bonds are forming, no structure. What do we expect to see? And if your only exposure to diffraction is Bragg theory, you have really no basis or framework to even to understand what the diffraction from a gas would look like. Well, it turns out that it looks like the curves are shown on the right-hand side, these bell curves. In fact, the black one is for oxygen. So this is the atomic scattering for oxygen. And the green one is for hydrogen. Now, I've plotted these on a normalized intensity scale, so I can actually compare the two curves together and look at their shape differences. Now, these are essentially the atomic form factor, F, although as in diffraction, we measure intensity, which is squared amplitude. So these are F squared, so the atomic form factor squared, and this is the atomic scattering for oxygen and hydrogen. Now, one thing you'll see is the hydrogen falls off much, much quicker as a function of 2 theta than oxygen. So hydrogen only really contributes to diffraction that occurs at relatively low angles. And if I was to put something like molybdenum on here, it would continue out to very, very high 2 theta angles. In fact, the rapid fall off of the atomic form factors for light elements is why when you're measuring pharmaceutical materials, typically you may only measure to 40 degrees, sometimes 60, or the rare case out to 80 degrees with copper radiation, because the atomic form factors fall off so fast that the diffraction signal more or less falls to 0 once you go up beyond 40 or 60 degrees 2 theta. So at 0Q or 0,2 theta, the value of the form factor squared is essentially the number of electrons squared for each atom, or Z squared, the atomic number squared if for a neutral atom. So we can do that for oxygen, and for oxygen, we do the square of the number of electrons, and we end up with 64. So a single oxygen atom would give us 64 on this intensity scale, and hydrogen only gives us 1, which is why I plotted them as normalized intensity, because scattering from hydrogen is 64 times weaker than the scattering from oxygen, single atoms, neutral atoms, which is the reason why when you do single crystal structures, it's pretty difficult to place the proton if you're using X-rays. Now, if you do electron diffraction, which we have electron diffraction systems as well, then the difference is about 1 in 30. So our sensitivity to hydrogen doubles if you use electron diffraction, which makes it a very useful tool for placing protons in crystal structures. So if you're doing salt co-crystal type of studies, then electron diffraction can help. Of course, neutron diffraction is even better. That is highly sensitive to protons, but then you'll need a crystal that's probably a few centimeters in size. So let's drop the temperature down. And now we start to form some bonds, in this case, double bonded oxygen, and this is structure. So structure is forming in the gas. We've got this physical relationship between oxygens. They have a well-defined distance between them. It's a reproducible structure, and it'll be commonly occurring in the gas once the temperature drops down to the appropriate level. And X-ray diffraction is a structural analysis tool, and as soon as we have structure appearing, you will start to see diffraction effects in the data. And no, you don't need crystals, you don't need lattice planes or anything like that. As soon as structure forms, even at the atomic level, just doubly bonded oxygen, you'll see that in the diffraction pattern from our gas that we're looking at. And the diffraction pattern is the solid line over here. And you can start to see some wiggly parts to that, which is the structure and the diffraction from that well-defined doubly bonded oxygen. Again, X-ray diffraction is not chemically sensitive. It doesn't know there's a double bond there. It doesn't even know that it's oxygen, actually. It's only sensitive to electron density, which would be an atom in this case, and the physical relationships between atoms, how far apart they are. And to see it in a diffraction pattern, again, it has to be reproducible, has to happen many, many times, and has to be commonly occurring in the sample. If that is present, then you will get diffraction structure. You'll see diffraction from the structure. And again, we have this ubiquitous atomic scattering, the sum over F squareds. Remember, F squareds are the atomic fingerprints, and these form the average of the diffraction pattern. So as you go to higher 2 theta, the pattern oscillates about this sum over F squared. And this is the heart and the essence of total diffraction, is the sum over F squareds, or the sum of the individual atomic scattering functions, gives you the mean scattering from a total diffraction pattern. And we can do the calculation here. We just have 2 oxygens. So the sum over the formula unit is just 64 plus 64. So that intensity scale is 128. And just for reference, this central point here is the forward scattering where it's all coherent. This is the coherent intensity profile, which is 256. So it's a sum over F's all squared. Now let's dig into that a little bit more and look into where these features are actually coming from. And the equation I've just popped out at the bottom. So this is the only equation that I'll show, that, so please don't just pass out and fall off the chair. This is the Debye total diffraction equation. And actually, at least to my mind, that's a pretty damn simple equation. That equation describes all of total diffraction from any material, from any diffraction process, providing it's a kinematic diffraction process. It's a very, very simple equation. Now let's break it down. It actually has 2 parts to it. The first part is the sum over F squared. We know that. That is the sum over the individual atomic scattering intensities. And this forms the average diffraction in total diffraction, the average diffraction signal. This is the actual coherent diffraction part, and that is oscillatory. It's got a sine function in there, so it will oscillate about the mean response. So if you average over all the diffraction response, pretty much it follows the sum over F squared curve. And that's how we are able to do standardless quantitative analysis using total diffraction. Of course, the oscillatory part is depending on D's or distances, distance between atom I and atom J. This is our 1.4 angstroms in the doubly bonded oxygen. And it's a pairwise calculation. So it's the sum over all atoms pairs. So all atom pairs, looking at all of their structures and distances between them, and it's just a straight linear sum. And the consequences of that we'll investigate later when we're looking at more complicated structures. In actual fact, it's just a linear sum of all the individual atom-atom contributions will give you the total diffraction pattern. Okay, let's drop the temperature a bit more, and now we're forming the actual water molecule, H2O. These again have a well-defined distance between hydrogens and oxygen. But when we look at the total diffraction from this, it's not very exciting. We don't see any structure as such. And that's basically because, again, the scattering from hydrogen is just 1 on this scale, and for oxygen, 64. So the hydrogen contribution is really, really tiny. So you're not really sensitive to the diffraction features because of this well-defined structure here. Let's drop the temperature a bit more, and we'll get to something more interesting. Now we form the first of the high-density water and the high-density materials formed by water, and it's liquid water. And in liquid water, you have a number of spontaneous, like dimers, trimers, hexamers, tetramers of hydrogen-bonded oxygen that form inside the water. These spontaneously form and break rapidly within the water, depending on the temperature that the water is held at. Now, X-ray diffraction is considered to be instantaneous. So even if these structures persist just for nanoseconds or picoseconds, you'll still get a diffraction signal from these structures as they form and break rapidly in the material. Again, in order to see them in a measured pattern, they have to be consistent. The same structure has to form, and it has to be present on average over the whole measurement for a large portion of the sample. And if that's the case, you will see a diffraction pattern from it. So the most common local structure that forms for water is these trimers, the hydrogen bonded oxygen triangles, if you like. And for a single trimer, this is the total diffraction pattern that we expect to see. Now we have really nicely defined diffraction halos in there. Of course, we still have the sum over F squareds. So that is the fingerprint that is in all total diffraction. It's the sum over the atomic scattering intensities for every atom in the formula unit. So in this case, 3 oxygens, 3 hydrogens. That's the sum over F squared. That is the mean and the asymptote diffraction signal. At high 2 theta, high Q, all diffraction tends to sum over F squared. At lower 2 theta, lower Q, it oscillates about that, and that becomes the average response. Now, in this case, I've arbitrarily divided the diffraction pattern, or the total diffraction pattern. And at the lower angles, we call it small angle X-ray scattering, and at higher angles, we call this diffraction. Again, this is very arbitrary. It all comes out from the same total diffraction formula. You do not need a separate formula to calculate SAX and another formula to calculate diffraction. They all come out from total diffraction. And the reason this is so dominant in this case is that we just are considering a single trimer. This is about a 3 angstrom nuclei of like dense water, if you like. So if you looked at a 3 angstrom dense nuclei, this is the small angle scattering you'd get from a 3 angstrom particle. Now, if we look at the actual diffraction pattern of water, at the bottom here, this is measured diffraction pattern of water measured on our instruments. And we'll come back to that later. In fact, we'll come back to this, I think, 3 times during the slide deck. When you look at actual water, you can see that we see these 2 halos corresponding to these first halos on the calculated pattern, but we don't see the small angle scattering. And that's because we're looking at bulk water, which is essentially isotropic. So that contains billions of these little trimers all together in this large bulk sample that fits inside the sample holder. So that will not give a strong small angle scattering signal, but you do see it when you do a theoretical calculation for a single trimer. Now, I always recommend that when people are doing total diffraction, that water, distilled water, is a good sample to look at. Although you'll need to put it into an airtight sample holder, and we have these sample holders for all of our diffraction instruments, so you can put water and you can seal it up, and that will keep it within the holder itself. If you don't have an airtight holder, the water will evaporate during the measurement, so then you'll have to top it up maybe 3 or 4 times before you can complete a total diffraction pattern. And this first halo, if we look at the measured data, actually occurs at 30 degrees 2 theta. And one of the reasons I recommend water is there's a nice symmetry to the story. It's a trimer. There are 3 oxygen atoms. The hydrogen bonded distance between the oxygens is 3 angstroms, and the diffraction peak with copper is at 30 degrees 2 theta. So 3, 3, 3. Easy to remember. It's a very characteristic fingerprint, and it's a test that your instrument's working well and that you can do total diffraction from disordered systems. So a highly recommended test if you're doing total diffraction. So let's drop the temperature a little bit more. And now we're forming an ice crystal nuclei is forming. This is only about 1 nanometer across. So this is a 1 nanometer ice nuclei crystal that's just crashed out from the water. And this is what the total diffraction pattern looks like for that, like 1 nanometer crystal. The small angle X-ray scattering has shrunk. It's gone in because now it's not 3 angstroms particle, but a 1 nanometer particle. So the SAX gets tighter. But now the diffraction patterns are getting a little bit more well-defined, more structure to them. It sort of looks amorphous-ish, but it has additional structure to it. Now, again, the sum over X squared, it never goes away. For any type of material looking at, whether it's crystalline, liquid, or gas, the sum over X squared is the mean diffraction response. And this is, again, the heart and the essence of total diffraction. It enables us to do what we do. It's what allows scaling to do PDF analysis, and it what gives you standardless quantitative analysis. Now that structure is looking a little complex, and it can be a little difficult to analyze when you just look at the pattern, when this additional complexity comes in as things begin to crystallize. So traditionally, the way that's been handled is with Bragg diffraction. So now I'm changing probably to the diffraction theory you're more familiar with, Bragg diffraction. because it is a useful conceptual tool to help you understand diffraction patterns when you start to get crystalline order. But it's particularly useless when you don't have crystalline order. So in this case, we have our 1 nanometer nuclei forms again. And the first step is to mathematically construct this conceptual idea of a unit cell that describes the parts of the structure that remain unchanged. And we define that with 3 lattice parameters, A, B, C, they're 3 lengths, and 3 angles, alpha, beta, gamma. And this is the unit cell for ICE1H, which is the structure that I've drawn there. So hexagonal ICE. ICE has many, many crystalline polymorphs. ICE1H is the most common one on Earth, but it's not the most common one within the universe. As we look at asteroids and we look at the water in them, they have a very, very different structure on space objects. So once we have the unit cell, we can construct some lattice planes. Then once we have lattice planes, we can construct some distances between parallel planes, these d values. And from that, of course, if I just extract out one set of these planes with a well-defined d value, we can get Bragg's law. So we have an incident X-ray wavelength lambda. Incident on one of these planes at an angle theta. It reflects, if you like, or diffracts at the same angle theta, so it's completely symmetric. And we assume we have a parallel beam, a plane wave of X-rays that are coming in, and it interacts with the plane below it. So a plane wave of X-rays and a plane in the crystal. And then for coherent diffraction to take place, these 2 reflected waves have to be coherent with respect to each other. And this is what gives you sharp, well-defined peaks. So in order to see peaks, these 2 reflected waves from different layers in the crystal have to be coherent. And to do that, the path length which is 2d sine theta is the path length different from the waves from the top and the bottom surface of the crystal here. They have to be a whole number of wavelengths. So this gives you Bragg's law, 2d sine theta equals n lambda. So that's where it comes from. And this is a mathematical construct that we impose on top of the crystal. And we do that because it really helps us to characterize complicated diffraction patterns. So now this is a slightly bigger nanocrystal of ICE1H. This is about 2 nanometers in extent. And the blue is an actual calculated total diffraction pattern from this 2 nanometer nuclei of water. And you can see it's sort of X-ray amorphous-ish, but it's definitely got some additional structure that's forming in it. And then when we compare that to the Bragg peaks calculated from the Bragg theory, now you can begin to characterize some of that structure. First of all, I'll point out, even for something like this, sum of S squared is the mean response and the asymptote of IQ. That's very important. And now with the Bragg diffraction, we can start labeling crystal planes and directions that can give rise to these features within the data. So Bragg diffraction for me is a conceptual tool that's useful to help us understand a diffraction pattern in terms of what atoms and planes are involved in the features that we're seeing within the data. But again, it is a conceptual model, and total diffraction is usually my go-to approach in getting a much more in-depth understanding. The reality is, using Bragg theory, using Rietveld, you could probably never describe this total diffraction pattern. You could add in arbitrary peak functions, make it broader. It's a 2 nanometer size crystal. I'll put in the peak size, and you can try and fit this data, but the reality is you'll never capture the entirety of what's present in this total diffraction calculation. Now, from the total diffraction perspective, we have our own ways of characterizing complex data. And I'm going to go through this in more detail again, so don't panic though, suddenly jump to a PDF. But the way we do it in total diffraction is through the PDF, pair distribution function or pairwise distribution function. And for this like 2 or so nanometer size crystal, this is what the PDF would look like. Now in blue, this is the total structure. So this is hydrogen and oxygen together. But in red, I only looked at the oxygen-oxygen distances. But one of the powerful things you can do with total diffraction is you can identify particular atoms you want to look at, and then you can isolate them in the total diffraction fingerprint. and in the PDF, that's commonly done. You'll see it in a lot of literature. They do partial PDFs of various atomic relationships to try and understand, which atoms are close to each other. And if you look at the blue one, there's all these structural features at short distances, which are due to the hydrogen, which are not present in, we just look at the oxygen-oxygen interaction. We can see the clear characteristics, the 4.5 angstrom, which is the unit cell size for ICE1H. So that's the size of A and B. And 2.75 angstroms, which is the nearest approach distance between oxygen. So in this way, we can characterize structures in what I would say is a much more powerful way than doing it through the conceptual Bragg approach. Now, you don't have to go to the PDF to do these partial total diffraction comparisons. You can do this on the total diffraction pattern itself, and then you can compare this to the measured data. Total diffraction is additive by each atom pair. So if you only want to look at oxygen-oxygen relationships, or hydrogen-hydrogen, or you've got a nitrogen and a chlorine, you want to see how they're related to each other, then you can calculate them separately and compare them to the measured data, because total diffraction is additive at the atom-atom pair level. Okay, we have our first poll question. We have 2 questions today. And the first question is, have you heard of total diffraction or performed total diffraction previously? And I think Stephen will now run the poll. So I think we're more or less 14 out of 22 of you have participated, and it's about 50-50. So half of you have worked with total diffraction or heard of total diffraction before, and the other half, it's something new. Okay, thank you. Let's move on to the next slide. And now we're going to apply total diffraction to look at some unknown materials. And some of you may have seen this example before, but because it was published back in 2013. But I think it is really one of the best examples of total diffraction as applied to unknown materials. So this is measured data that was collected on a series of Lyra files that were taken from a freeze drying cycle using thief sampling. And this was all done at Baxter Healthcare by Steve Nail. And what he did is he thief sampled different Lyra files at different stages of the drying cycle. So the hypothesis was that these contained very, very different amounts of water in the individual samples. And these are what the total diffraction patterns look like. Now, total diffraction, as you do it in the lab, is somewhat different from Bragg diffraction. Now, when you want to do Bragg diffraction, your focus is looking at peaks. So to do that, you tend to improve the instrumental resolution. You have small slits, big radii. You may even go to a synchrotron, so you can separate out individual peaks to make your Bragg analysis easier. In total diffraction, we sort of go the opposite way. We relax the optics, we open things up, because we want to collect the total diffraction signal from the sample. The data collection is much the same. These are all theta-2 theta scans or theta-theta scans. But with total diffraction, typically we open the optics up. With Bragg diffraction, you typically close the optics down. So these are typical diffraction patterns. There's a lot of variability in the data here. And some of that comes from differences in sample mass or changes in the instrument that adds all this spurious variance to the data that makes it difficult to identify what are the actual signals due to the presence of water inside the sample. So we have to go through a pre-analysis or pre-data treatment to present the data in such a way that we can do total diffraction analysis. And essentially that's removing the spurious variance. We're removing the variance because of change in sample mass or differences in sample prep or changes in the instrument. We want to remove those. And the first way we do that is we remove a calibrated instrument background. Now, this instrument background for total diffraction is not the background you'll get from your peak searching or Rietveld approach. Those backgrounds are for Bragg approaches, and they're completely useless for total diffraction. So you have to measure and calibrate your profile on your individual instrument. And if any of you need guidance for that, reach out to me and we can go through that in detail, how you determine the true instrumental background. So in this presentation here, I'll remove it. Actually, in practice, I leave it in the analysis. I don't like taking data away, but for ease of illustration, we'll show the data removed. Once we've removed the background, we then scale all of the patterns to common area. And again, this is the standardless quantitative approach we covered in the first lecture. Again, the area is the sum over f squared, it's total diffraction, they must be the same. And so we normalize everything to the same common area. And we minimize the standard deviation between all of the data sets that we've collected. And what you'll see as we do this is that higher 2 theta or higher Q, everything approaches the same asymptote. Again, that's total diffraction. It's called the binormalization. At high Q, everything has to approach the same asymptote. And at low Q, in the absence of small angle scattering, all the diffraction signals should go to 0. So if you like, there's pinch points at low angle and high angle. And the actual variance due to changes in the sample is captured in this medium region here. This is the final data sets. If you remember when we started off, they were sort of a mess. Now we've gone through our normalization, our pre-treatment. We've applied total diffraction theory. If you like, it's a Bayesian approach. So we sort of know things about what the diffraction should look like. So we apply that to the data. And this is the actual data we're going to analyze to try and understand the impact of water inside these lyophiles. Now, this was done in 2013 when we didn't have the latest version of SmartLab Studio 2. So I did this analysis in the statistical programming language R. That's still available if you want to try that for yourself. And this is variance analysis in R using either PCA or PLS type of approaches. When I pass that data ensemble through, it tells me that I have 2 variance components which are orthogonal. And it turns out this blue-green one here is for the lyophile matrix, and the red one is for the water that's added into the system, or the variable water content. So we can take these variance components, these 2, one for water, one for the lyophile component, and we can fit them to the measured data sets to fit the variance in the data. And this will give us a scale factor for the lyophile, scale factor for the water component. And then we can compare those scale factors against the known water concentration, because at Baxter Healthcare, they have a calibrated IR technique for all the samples to pass through to give us some idea of the total water content. Now, what you'll see is that the scale factors of the lyophile in blue and the scale factors of the water in red, they're linearly correlated with the known water content. So this tells us that X-ray diffraction is linearly sensitive to the amount of water within the samples and can be used for both ID and quantitative analysis of water in the material. Now, when you look at the amount of water that was there, you'll be shocked. The lowest concentration is 0.13% weight. So this shows us that we can construct a quantitative technique to determine the amount of water down to 0.13% weight in a totally amorphous sample. There are 2 amorphous components together. Just a few years before this, the accepted wisdom was that you can't use X-rays to quantitate amorphous material. Well, obviously that's complete nonsense. We can go down to extremely low levels of amorphous and amorphous, even for multiple amorphous components. You may have an intermediate you're working with, an amorphous solid dispersion. It may have 2, 3, 4 different components in there. With X-ray diffraction, you can identify and quantify these components, which can be a really good indicator of warnings of crystallization when they begin to phase separate in your intermediate. Now, an alternative approach is to project out real components instead of variance components. To me, variance components are somewhat confusing, and they were only used in 2013 because it's all we had. But now with SmartLab Studio 2, the current version, we can actually extract out real components, which to me is a lot more interesting. And it again identified 2 components in those samples, just 2. The blue one is the lyophile matrix, and the red one is supposed to be water. Well, You already know what water looks like. We talked about that. It's very well known, characteristic. One halo at 30 degrees, one halo at 40 degrees using copper radiation. I look at the orange curve here. There's no halo at 30 at all. So although the orange is capturing the water variability in the lyophile, it's not water that's giving the structural fingerprint. So from this, we know absolutely that water is bonding to a part of the lyophile. It's forming a characteristic structure in the lyophile cake. And we actually went back and did some reverse engineering and chemistry on that. And we identified that the water was bonding to sucrose and forming a 2-to-1 sucrose water like syrup inside the material. So the water that was present in the lyophile was not free water. It wasn't puddles of water either. The water was actually chemically bonding to the sucrose, forming these 2-to-1 ratio syrupy mix inside the lyophile itself. And apparently 2-to-1 sucrose water ratios is very, very common in nature. There's a lot of naturally occurring syrups like agave, for example, that have that same 2-to-1 ratio between sugars and water. So it's a frequently occurring structure. So in this way, we use total diffraction and component analysis to not only quantify water in an amorphous system, multi-component amorphous system, but also to identify chemical changes that were going on, different bonding relationships inside an amorphous structure itself. Now, in my mind, this is unprecedented for diffraction. This is absolutely not possible with traditional approaches. You wouldn't even have a framework to do something like this. So this is a very powerful application. And this is supported in the new version SmartLab Studio 2. So it will enable you to do this sort of analysis in the lab. So now I'm going to change directions a little bit. And we're going to talk about PDF small box models. We have a little bit of time left, so we'll go through this rather quickly. And we have a second poll question coming up, Stephen. And this question is, have you performed PDF analysis previously? So have you actually measured and calculated PDF profile? So the poll's up now. If you'd just like to vote on that. So we get some idea of who's doing PDF analysis. And it looks like more of you have done that, about 60-40. That sort of surprises me. So more and more people are doing PDF analysis now. That's actually pretty exciting. I think moving forward in pharmaceutical sciences with the new formulations we're seeing and nano delivery systems, you'll be seeing a lot more of PDF and total diffraction, really. So that's great. Thank you very much. So the first thing I want to do is like give you a conceptual overview of pair distribution functions, how they're related to our measured total diffraction, and how they're related to the models that we build to describe them, particularly small box models. So this one, again, I said we're only going to talk about small box models. There are big box models, which are perhaps more common in the literature. And we have big box modeling capabilities in SmartLab Studio 2, using reverse Monte Carlo, either from random packing or starting from crystal structures. What I'm going to talk about now is small box models, which is usually my preferred approach. So if we start off with a small box model, which is one molecule, it doesn't get much smaller than that. And this is indomethacin. And this is taken to represent an amorphous material. So our first approximation to what is an amorphous material in terms of structure is the only reproducible structure is the molecule. Nothing else. It's just completely random, let's say. That's our hypothesis. Then from our small box molecule of a small box model of a single molecule, using the Debye total diffraction, that's the formula I gave you earlier. And you can do this in Excel. It's really simple. You can program it in Excel. SmartLab Studio 2 will calculate this for you. And I believe it's one of the only commercial programs that can calculate the Debye total diffraction from any given molecular model. So from this model, using the total diffraction, we can then calculate what the total diffraction should be, and we can compare that to the measured data. And this is the measured data of glassy indomethacin. This was collected on one of our SmartLab units using molybdenum radiation with a spinning capillary. And we can also directly calculate something that's called QS of Q minus 1. That's a pretty oddball name, but it's a very, very powerful representation of the data. And it's essentially based on the reduced structure factor S of Q, and it can be directly calculated from measured data. It's very easy to calculate. There's no real manipulation of the data required. It's just a simple scaling and calculation, and you get QS of Q minus 1. And you can also directly calculate it from the molecular model, from the small box model. Again, SmartLab Studio 2 will do that for you. It'll give you the measured and calculated QS of Q minus 1 in the latest versions of SmartLab Studio 2. The next step is PDF. Now, a PDF, to get there, you have to Fourier transform QS of Q minus 1. So it's a Fourier transforming step. But from our molecular model, we can actually calculate it directly again. This is using this atom-atom histogram approach, which is sort of an approximate approach, similar to Bragg theory as a conceptual approximate approach. But this is the approach you'll find in most programs out there, like PDF GUI, for example, and most analysis software will do this direct calculation using this atom-atom histogram. In SmartLab Studio 2, we can go this other way through the Debye calculation as well. But then you've got to go through the Fourier transform. Most of the time, as I've mentioned, I prefer to avoid the Fourier transform because you have to manipulate the data to get there. And it seems to make it almost laughable. You spend so much care to collect the total diffraction data that you then have to manipulate it to get the PDF out, which is not ideal in my mind. So let's go through that analysis in a bit more detail. I'll have to skip through this because I'm running out of time. So this is indomethacin again. This is a measurement of glassy indomethacin that are done on one of our SmartLab SEs. The SE is the baby SmartLab, which is a special edition for powder, using molybdenum radiation and capillary geometry transmission. So how do we scale that to give us the total diffraction signal? Well, in gray, this is our measured total diffraction. This is the data I just showed you in gray. And blue is the Compton scattering. And then we scale the measured data to this sum over F squared. So this orange, that should be very familiar to you now. That's just the sum over the atomic scattering intensities. And we scale the measured data to be asymptotic to that at high Q. So you can see the measured data is asymptotic and follows very close to the sum over F squared, which is what we expected. And just for reference, in green is the Debye total diffraction. Now, I prefer to look at that in QS of Q minus 1. This is mostly where I do my analysis. And now it looks actually really, really interesting. So the blue is the QS of Q minus 1 for the measured data. Simple calculation, very easy to do. And red, this is the Debye calculation based on a single molecule. Remember, our hypothesis was the amorphous material is described by just the structure in one molecule, no other structure present at all. It's just random. Now, at high Q, so from 6 and beyond, so Q of 6 out to 18, the Debye calculation fits the data very, very well. So at high Q, the structure you're looking at is essentially the rigid molecular structure of a single molecule itself. At lower Q, at 6 and below, and remember with copper, you can probably measure out to Q of 8. With molybdenum, we're out to about 17.5, I think, something like that. If you go to silver, you can go out to, I think it's like 24. But at low Q, below 6, which you can access with copper radiation, you can see the difference between the Debye calculation in red and the measured is vast. So we split the data into two parts. At high Q, it's the molecular fingerprint, the rigid structure of the molecule. At low Q, this is the structural fingerprint. This is the packing of the molecule inside the glass, or the amorphous dispersion. This is how the components are linking together in the amorphous dispersion. All of that you see at low Q and can be measured by copper in the lab. The high Q is the rigid structures inside the individual molecular entities themselves. So let's go through some examples where we model this to extract out the molecular packing function. So let's start off with nifedipine. And on the right, this is the PDF of glassine nifedipine. Again, these were all done with molybdenum radiation on the SmartLab SE using capillary geometry transmission. So from the molecular side, we can calculate a molecular PDF. Again, in total diffraction, everything is additive. So if you have one part of the structure, you can calculate it, and then you can add in the other parts of the structure later on. All of these things are additive, so you can start from simple and then build up complex models. So we add in the molecular fingerprint into the PDF, and then the missing part, which is not described by the molecular fingerprint, is then described by this molecular packing function. So this is a component approach again. We have two components, a molecule and a packing function. We can combine them together to fit the PDF data itself. So this is using small box component analysis to give you this local packing structure inside the glassy material. For nifedipine, it's a very well-defined structure. We have nearest neighbor, next nearest neighbor, next nearest neighbor relationships. But if we go to simvastatin next, a more complicated material, the packing function is totally different. Here we simply have what used to be called in the bad old days an exclusion zone. What we mean by an exclusion zone is that each molecule essentially has like a hard sphere around it, so molecules can't intersect. So individual simvastatin molecules don't drift into each other or through each other. There's an exclusion zone around them where molecules can't get any closer to each other. And this exclusion zone, covers around about 4 angstroms or so for simvastatin. And again, the same approach, small box, molecular fingerprint, and a packing function combined together, very simple to describe the PDF. These are very simple analyses, but they give you a wealth of information about packing and relationships in the amorphous state. Now, the last slide I'll show before we open, we'll go through some of the questions. I think we have 7 questions or so in the chat. And this is looking at the higher Q range, the molecular fingerprint. So to get this higher Q range, you're going to have to go to molybdenum or silver to do those measurements, because this is a higher Q where you see the molecular fingerprint. But the accepted wisdom, again, for amorphous materials for organic molecules is that a molecule is free to explore all possible conformations allowed to it at that temperature. So like a Boltzmann distribution of all conformations. So the molecule will twisty in the amorphous state. You're going to have all these different conformations. But that's not what we see a lot of the time. So in this case, we took indomethacin and we generated hundreds of different molecular conformations of indomethacin as allowed by ambient conditions and the Boltzmann distribution around that. And then we compared them all to what we actually saw in the measured data, because we have the molecular fingerprint, we can see it. And it turns out there's only one unique conformation of indomethacin that describes the measured data. And it turns out that is the conformation that exists in the gamma crystalline polymorph of indomethacin. So again, it's a really surprising result. And we've done this for many materials now, looking at the conformation in the amorphous state. And it can be very surprising what comes out from that. And in this case, the conformation is the polymorph that's stable at the highest temperatures. And that's something we commonly see, that the crystalline polymorph that's stable at high temperatures imparts its conformation onto what we see within the amorphous state. Now, this is, again, totally against the accepted wisdom, but this is looking at the data. These are the numbers that we see coming out. Well, I hope I've whetted your appetite for total diffraction and how we can use this for analyzing amorphous materials to get a wealth of information that you might have thought was completely hidden to you and you couldn't extract. This is just the baby steps. We can go a lot deeper than this. And again, if you'd like us to come and give us a seminar, or you want some assistance in getting started, then please feel free to reach out to us. So during this webinar, we've discussed total diffraction, the water story, the basis of total diffraction. We've applied it to unknown amorphous mixtures to isolate when we have a particular preferred bonding relationships forming where things are truly miscible at the molecular level compared to immiscible or phase-separated systems. And we've done a very quick walk through PDF small box methods. If there's sufficient interest, we can do some of the big box reverse Monte Carlo stuff. It'll be next year now in the next set of webinar series. And so please reach out if you want us to talk about big box methods. In fact, if you have any suggested topic for the future series of webinars, absolutely reach out and suggest some topics for us. So again, thank you all for bearing with me for the last 45 minutes or so, and we'll open the floor to questions.
All right, thanks, Simon. We do have time for a short Q&A. We've had a couple of questions come in, and I got a couple of questions as well. So the first question is, how sensitive is a diffraction pattern to the amorphous sample structure? So, for example, can you see the difference between distilled and salt water?
That's interesting for water. Hopefully, I've shown you that it's very, very sensitive to structure. Diffraction is a structural probe. So if the sodium chloride or some part of the salt is forming a structural relationship with the water molecules, then absolutely you will see it. If it's just suspended solid, then that's less likely you're going to see a distinct structure. But if they're forming some sort of intimately bonded structure, then you'll absolutely see it. As in the lyophile, the water bonded with the sugar to form this complex saturated goo, and you could clearly see that. So if it forms a new structure, if it's there at a reasonable level, we've already said it's got to be there above about 0.2, 0.5% weight, then you will see it. Absolutely.
Okay. Okay. So I had a question actually, and I didn't notice this earlier. So you said that you have to run it in water in a sealed container. How long is that total diffraction experiment for water in general?
Well, the first time I did this, I ran it for many hours just because I wanted to get out to really high Q. And as you go to higher and higher 2 theta, the signal level drops. So when you convert it to QS of Q minus 1, the noise can become terrible.
Right.
So
right.
usually you got to collect data for a long time if you want to do total diffraction work at high Q. And I actually break the data down into sections. So I collect the low angle data for a very short period of time. And as I go to higher Q, I then increase the count time. In total, it was probably 3 hours.
Okay. Okay.
And the water evaporates in probably 20 minutes or less, 10 minutes.
Interesting. Okay. Okay. All right. This next question is related to PDF in general, right? So you mentioned copper, molybdenum, silver. So they all cover essentially different ranges. Is that right? Can you kind of just go through that real quick one more time?
Yeah, sure. For laboratory instruments, there are a number of standard X-ray tubes you can choose, which defines the X-ray wavelength. The most common ones, at least for total diffraction, are copper, molybdenum, and silver. And there are various reasons for choosing each of those wavelengths. Again, the traditional wisdom is that for total diffraction, particularly PDF, then you want to have shorter wavelengths, higher energy X-ray. So you'd probably wander up towards silver if you followed that narrative, or go to a synchrotron, or actually, in fact, do electron diffraction where the wavelength is 0.025 angstroms. But in practice, in the lab, my experience is that molybdenum is the best bet because it gives you sufficient access in Q, about 17.5 in Q. You can clearly see the rigid molecular structure coming out. You can clearly develop that and model the molecular structure. And molybdenum is still relatively well scattered by organic materials. By the time you get to silver, it just passes through organic materials, and your scattering signal is extremely low. And I don't think the extra Q going out to 22 or whatever it is worth the loss in signal strength that you see. Plus your diffraction pattern shrinks to low angles. And for most organics, they have a lot of low angle structure anyway, a lot of low angle peaks. If you have D values, 15, 20, 40 angstroms maybe, then those peaks occur at low angles. Even with copper, you might be down at 3 degrees, 2 degrees, 2 theta. If you go to silver, you don't see the low angle peaks. They occur so low that on standard measurements, you don't pick them up. So there are 2 reasons why I don't like silver so much. It doesn't couple well. Signal level is very low, so at high Q, it's basically all noise. And also you miss the low angle peaks. Molybdenum seems to be an ideal compromise to me.
Okay. Okay. Thank you. Thank you. All right. So Simon, that's all the questions that we have. Okay. So we can kick on to the next slide.
Okay, just give me a second.
Yeah. All right. So Yeah, so again, as Simon said, this is our final webinar of the year. And if you missed any, please check out the entire series thus far via the link that I'm about to drop into the chat window. Simon also provided links to that will also be on the landing page tomorrow and are also in the chat currently for the resources that he's referenced at this time. All right. The next slide is, and as I said earlier, a recording of the webinar will be available and an email will go out to all registrants on how to view the recorded presentation. And again, as I just mentioned, links to these resources will be shared on that landing page. Simon, you want to kick forward? Is this your final slide, Simon? I can't remember if I had one more or not. Okay. We'll go to the next one is you can find Simon on LinkedIn. If you go to linkedin.com/in/Simon-Bates, you can connect with him there and continue the discussions. And finally, again, thank you all for attending, and we look forward to seeing you again next year. Have a great afternoon.
Yep, thank you all. And until next year, I'll sign off for now.
Thank you. Bye-bye now.
Bye.